All right. Hi, everyone. Welcome to the keynote session on safety and formal methods. I'm Hadas Gazit. I'm a professor in mechanical and aerospace engineering at Cornell University. And it is my pleasure to chair this session. I want to take 2 minutes to just talk about what safety and what formal methods are, kind of. I think you've probably heard the word formal methods. Sometimes people are like, okay, what is it actually? So this is the definition that I like from a paper from the formal methods community. And the idea here is, well, the definition here is mathematics-based techniques for the specification, development, and manual or automated verification of software and hardware systems. So the main things here are it's mathematically based, and we have the word verification. I would also add the word synthesis of generating a system correct by construction and all these things from specifications. So that's the definition for formal methods. Safety, I am going to leave that open because I think none of us really have a good definition for what safety is, and that's kind of a research topic in the community, which is very exciting. So if you disagree, come and fight me later. And when I bring safety and formal methods, and we're talking about robotics. So how do these things apply to these physical systems working in crazy situations outside in the world with people around them? And what can we actually verify? What can we actually synthesize? What are these specifications? Those are the questions that come up from this subcommunity within robotics. So today, we have 4 wonderful presenters. I am actually not going to give a long introduction for each one of them. I want to kind of keep the time for questions. Unfortunately, 2 of them couldn't be here, so we will see their recorded talks, and they are online on Zoom for answering questions, so please still pay attention and ask questions at the end. And we're going to see different perspectives of what formal methods and safety mean in the context of robotics. What is the interplay with learning? What is the interplay with people? And how do we think about all these techniques? So without further ado, we will start with Professor Chuchu Fan from MIT.
Hi, everyone. It's my great pleasure to be here today to tell you some recent work we have done on large-scale safe autonomous systems or safe robots using control certificates, specifically graph control barrier function in this talk. So control certificates, they are control theoretical analysis tools for users to verify system properties or find controllers that satisfy these properties. For example, Lyapunov function is a very important tool that people use to certify the stability of a control system, especially the nonlinear ones, to be stable around a fixed point, or sometimes called the equilibrium point. Barrier functions are getting very popular these days to find safe controllers. So these certificate functions can serve as proofs for systems without asking to solve the system dynamics explicitly. Instead, they ensure the desired system behavior using inequality conditions. And those inequality conditions are much easier to analyze and to enforce than explicitly solving the system dynamics. If you're not familiar with those, let's start with a toy example where I have a robot, or more specifically, a helicopter that is trying to navigate around and avoid this dangerous mountain area. So control barrier function, or CBF, will take the state information and the environment information, output a scalar value that is positive for the safe states and negative for the unsafe states. So this 0 sub-level set here really creates a barrier between safe and unsafe. The reason it is called a control barrier function, not just a barrier function, is because the CBF can be used to compute the allowed input for the system. For example, in this toy example, we have CBF that can give us the allowed velocity of the helicopter as a function of distance to the mountain area. Of course, when the safety conditions change, the CBF should also take into update the updated safety conditions. For example, if that area in front of the mountain are experiencing strong wind now, we should have a new CBF that gives us the updated allowed velocity to keep the helicopter also outside that mountain, that windy area. So CBFs are good, so are the other control certificates, but usually people will have to handcraft them for specific systems. In general, there's no computational tool or effective computational tool that can find CBF for complex systems, especially for those with nonlinear and high-dimensional dynamics, or sometimes we don't even have the model information. Input constraints, complex safety conditions, especially those that are not distant to the obstacles. And in a multi-agent system, when we can have an arbitrary number of agents in the environment, they all pose significant challenges to finding CBFs. So as for the other control certificates. So in the past couple of years, my group have been working on something called the learning neural certificates. And the idea is to blend the control certificates into the machine learning process, both in supervised learning and reinforcement learning. We have stronger and stronger evidence to show that blending control certificates in the learning process can bridge the gap between model-based rigor and data-driven efficiency. So let's take a look at a representative case, graph control barrier function, or GCBF, for multi-agent system. I have a multi-agent system here where the blue agents are trying to navigate to their destinations, which are green dots connected to them. They only have local observations, which means that they can see each other or talk to each other when they're getting close. And when they're getting close, they may have a communication channel that they can start to talk to each other. They can also only use local observations like LiDAR to detect the surrounding obstacles. The reason these agents are navigating safely to their destinations is because of the GCBF underneath it. So the GCBFs, which are learned as graph neural networks here on the right-hand side, they can provide distributed controller for each of the agents. So that's really what is behind the scene to make the agents being able to safely navigate. And on the right-hand side, the contour there is a value of GCBF for the agent with a star. And of course, each agent will have their own GCBF. They will give that local distributed controller with local observations and consider input constraints. Together, all the GCBFs for each agent can give us a global safety proof that we can use to certify the safety of the entire system. And on the right-hand side, I'm also plotting the lines with a thickness value, which represents the graph attention each agent is paying to their neighbors. The thicker the lines are on the right, it means that agent is paying more attention to that specific neighbor. So we know that GCBF in learning process can make the controllers explainable, as I have just shown before. They can also make it scalable and generalizable. When we train those agents with eight agents in the environment with a distributed controller deployed on the more agents in this environment, so we can, in theory, deploy it on an arbitrary number of agents, of course, with the same dynamics. If you change the dynamics, you will have to get a new GCBF for that dynamics. So in the video here on the right, I'm showing more than 500 robots, and they all navigate safely to their destinations. So the controllers are also trained without explicit models of the obstacles in the environment. This allows the agents to navigate in the environment with obstacles that they have never seen before. So on the right-hand side, you can see the obstacle distribution is definitely different from the left ones. The learned controllers are also very robust in the sense that we can train them in simulation and directly deploy them on hardware across many different tasks. So here I have the drones switching their docking platforms or swap their positions in the formation in the presence of adversarial agents or big static obstacles that they have never seen before. They could also work collaboratively to monitor a moving spot without bumping into the moving spot, as well as not bumping into each other. And in that last video there, we can also visualize how GCBF is working to guarantee the safety. So GCBF or neural control certificates, they not only make the robots safely navigate to their destinations, actually they're more powerful. They can make safety no longer a competing objective in safe optimal control. In optimal control, we usually have an objective. For example, we need an airplane that navigates through the very narrow mountain canyon and keep a low altitude. Or we may have to ask a delivery drone to navigate in the city with changing wind condition and with a limited battery. Or we have inspecting robot that have to find the target and keep tracking the target to make sure they can observe the target at all the time. So in all these different tasks, the robot will need to satisfy the objective that's describe the overall goal or the mission. And in the same time, they need to be safe and respect their physical constraints as well as system dynamics. If I translate this into a multi-agent setting, that means we need to get a distributed policy that will be able to allow the agents to minimize a global cost. So there would be just one cost describe the overall mission, but the robot will need to figure out their specific actions to finish that mission together. Potentially, these agents will have only local observations, and we have a hard constraint that says all agents need to be safe, as well as satisfying the system dynamics, which can also potentially be unknown. Traditional methods like Lagrangian duality, they will make these hard constraints like safety or system dynamics into a soft constraint. As a result, the optimization problem or the optimal control problem will have multiple objectives. And if you use RL with multiple objectives, you will see that often in the case, these objectives will start to compete with each other. So we need to find a trade-off. As a consequence, these agents may have some safety violations, or in other cases, they may become too conservative, so they cannot finish the objective or finish their mission. Now, how does GCBF help here? Our key insight is that forget about the other things. Let's assume that H being positive is the safety constraint. Then a constraint value function VH that is taken the minimum of H over the infinite horizon is a legit CBF for the system. If this small h only take the local observation, we can also prove that the minimum of H is a legit GCBF for the partially observable multi-agent system, which means that if we can blend this constraint value function in the RL process, we will naturally have a GCBF to guarantee the safety. On the right-hand side here, I have a video showing the VH for the agent with a star. You can probably tell that it looks very similar to the GCBF we have seen before, and in theory, we can also show that this VH satisfies the three inequality conditions for barrier function. As a result, now we can blend CBF or GCBF naturally into the RL process. Safety is no longer a competing objective. Instead, there are hard constraints, while RL is here to help find the optimal policy among all the policies that satisfy the safety constraint. So across different multi-agent tasks, if we have GCBF here, we can see that the result will achieve the minimum cost for among all the results that can give us the highest safety rate. So it really gives us the best trade-off to have safety as a hard constraint. As a final thing, I want to zoom into the specific scenario that we are looking at. Two inspecting robots are trying to find the target and keep monitoring the target. So this target drone will move in its own pace, and the two control drones will need to keep up the target and keep this target in their observation cone. The goal, the overall objective is to maximize the time of the target being seen by at least one of the drone. And when it's being seen, it is shown in green. When the target is not observed, it is in yellow. Both the agents have to be safe, meaning they cannot get into the keep out zone of the target. They also have to stay away from the static obstacles. So if we have RL, GCBF in the RL process, as a result, we can see that one agent starts to approach and observe the goal. Now that agent, left agent, can see it, But when the left agent's view is blocked, the right agent know when to pick it up. Remember, they only have local observations and local communications. When they are getting too far away, they cannot talk to each other. So when it's difficult for the left one to observe, then the right one can naturally pick up. And going so on and so forth, we can see the agent is also always being observed. As a summary, I introduced the neural certificates, specifically GCBF, trained as a graph neural network. We believe they can bridge the gap between model-based rigor and data-driven efficiency, especially for systems with nonlinear and high-dimensional dynamics, with systems that we do not have the model information and have to use reinforcement learning. And we consider input constraints, complex safety conditions, and multi-agent system with an arbitrary number of agents in the system. A key limitation of the neural certificates, including the learned GCBF, is that there's lack of formal verification guarantees for these learned ones. However, it is important to note that verification of the systems, of these above systems with nonlinear dynamics, high dimension, or input constraints in general is computationally intractable or even undecidable, meaning they just cannot be verified. And the real-world systems often fall into these specific categories, not the simplified assumptions. So fundamentally, this is a trade-off between scalability and verifiability. As of now, we are prioritizing the scalability and generalizability aspect. In the future, we want to explore some hybrid approach that can better balance the data-driven flexibility with some provable guarantees, most likely in a probabilistic sense. So this work, especially the GCBF work, here I presented today, they are led by my students Songyuan Zhang and Swing So. They are both at ICRA, and we're collaborating with a lot of other teammates inside the group and outside the group. You're very welcome to talk to them. As you can see, actually a lot of them are here at ICRA. You can also feel free to check out our group websites, therefore a lot more interesting research. Thank you.
So we have a couple of minutes for questions. If anybody wants to line up, there are 2 microphones over there. And while that happens, Chuchu, I have a question. Mm-hmm. So you touched on this, right? So there's the learning CBFs versus manually designing them. The learning has this gap between, are you actually learning a true CBF? In kind of all the examples that you've shown on things you've been playing around in the lab, where's the gap? What do you see when you practically try to run this? Is it like it doesn't matter, or there are some edge cases that I'm just kind of curious to see what it looked like.
Yeah, definitely. So the question is how large of a gap the verifiability and the learned one. In terms of empirical performance, we do see the best empirical performance. So in the multi-agent is flying like robots or ground robots there, we observe that when we keep the density of the multi-agent system roughly the same, it pretty much generalizes all the way. But if we increase the density, it's naturally become a more and more challenging environment to navigate. Then we start to see the agents are not unsafe, but they are stacking at some local. There could be deadlocks there, and because of the safety constraints, the agents may stuck there. So in general, first of all, I encourage people to use a handcrafted CBF if they can, but for the systems that we are looking at, I don't think there's any good way to handcraft one. And the learned ones do have a pretty good performance, and if we calculate it, it's always like 99% something. Of course, there's that gap there. We'll have to figure out new approaches to figure out where the gap is.
So it's mainly deadlock that you see?
Yeah.
Interesting. Mm-hmm. Cool. Yeah, please.
Thank you for your talk. That was super interesting. One question I had when you mentioned having safety as a hard constraint and not having it competing. Often a reason for softening that constraint is because you might accidentally make those traits so strong that you're not able to complete the objective. Mm-hmm. Could you go into more detail of if that's a limitation or a weakness in this system or something you need to worry about, or if your system's able to handle that?
Yeah, so often the case we have to make safety or soft constraint, the things like relax a little bit, and then we will have multiple objectives in the whole objective function. We'll have to kind of balance the different parts. Often the case we see that if we penalize too much on the safety, then they start to become very conservative. That doesn't mean that they're not safe. They could be safe, but they cannot move forward to finish their goals. So the way we are having here is to tell you that the constraint value function itself is a GCBF, and because we have this value function, we can naturally have those in the RL process. Now, specifically how it works is it's the constraint value function, of course, is being learned simultaneously in the RL process. It's going to monitor whether your current action towards optimization of the objective is safe or not. If not, it will try to do a projection to take a step forward to make sure it is being optimized, the gradient is taken into the direction that both optimize objective as much as it can, but it really needs to satisfy the safety that in the constraint value function.
Thank you.
Okay, so a quick question, a quick answer, and then we'll move on.
Oh, thanks for the great talk. I have a question regarding the GCBF. When you deploy the policy, if it's gonna possible to get into a dialogue, for example, especially when the obstacle is concave rather than convex.
You mean like when we deploy it, the contour itself?
Deploy on the environment, and there may be obstacles, maybe not like a circle, like
I see. Yeah, that's a good question. So there are two things. One is the first, when we train it, we don't really assume any shape of the obstacles. So actually directly sampling from the LiDAR point, like they're all point obstacles. So they are LiDAR point rays. It is if we just use GCBF, it is possible that if we have like a non-convex obstacle, it may stuck at the non-convex part. That's because the safety will say you have to stay away from it, but the objective may ask you to keep closer to that part. But the RL part, where we have some examples where all the agents will have to go through some very narrow corridor. And if we train in the environment, in the training environment, we have seen this before, it seems to have been able to address this problem pretty well in the sense that we have the objective to get through, and that objective is being optimized with all the hard constraints being satisfied.